Okay, this tutorial is an overview of using the ideal gas law equation, as well as talking about a little bit of stoichiometric calculations using the molar volume of gas at STP. So if you look back at your notes, we said that STP is standard temperature and pressure. Okay, and that's 0 degrees Celsius and 1 atmosphere. Okay. 0 degrees Celsius is the freezing point of water, so that's not typically a temperature that we're working at, but we know that gases always have a volume of 22.4 liters at STP. Okay, this was something that was discovered by Amedeo Avogadro. He noticed that no matter what the gas was, we had the same number of particles present. Okay, so no matter what gas we have, if it's 0 degrees Celsius and 1 atmosphere, the volume will be 22.4 liters. So when we're using this ideal gas law equation, we're making a lot of assumptions. So if you look back at your notes, we talk about kinetic molecular theory, and there are some assumptions we need to make to use the ideal gas law. There is no such thing as an ideal gas, but gases behave approximately as if they were ideal, so we can assume that they're going to behave the same way when we work at temperatures and pressures that are not standard, okay, that are a little bit more realistic for us to work with. Okay, and we do this just to simplify the chemistry. This is an introductory level chemistry class. If we were to ignore those assumptions, the math gets a lot more complicated. We're going to start bringing calculus into play. So let's just keep it simple. The question says, what is the pressure in atmospheres exerted by a 54.0 gram sample of nitrogen gas in a 10.0 liter container at 298 Kelvin? So this question differs from the ones we were using before. In this question, you only see volume once. Pressure is only mentioned once, and temperature is only mentioned once. So we know we're not dealing with a before and after equation, so you are not going to be using the combined gas law or any deviation of that. Okay, so the ideal gas law equation says pressure times volume equals moles times the gas constant times temperature. So if we are using the gas constant, 0.0821, okay, there's particular units that we need to use. Pressure will be in atmospheres. Volume will be in liters. Okay, N represents moles. And temperature is Kelvin. Okay, so this is atmospheres, liters per mole, Kelvin. Whoops. Okay. So let's outline our information. So the amount of the substance N is given in grams, which we already know we need to convert into moles. I'm going to make note of that right here because the equation calls for moles. We're always going to use the same value for R. There is another constant that we can use dealing with different pressure units, but for right now, let's just stick with atmospheres. Okay, and we are given the volume, 10 liters. Okay, I know it's volume because it's given in liters, and temperature is 298 Kelvin, so we don't need to make any conversions there. Okay, and we know that we are looking for pressure. So if you outline all the information first, it's going to make it very, very easy to figure out where you're going to plug things in. So first of all, let's convert grams of nitrogen into moles of nitrogen. Okay, nitrogen is a diatomic element, so there's two of them. If I have grams of nitrogen on the top, grams of nitrogen goes on the bottom. Remember, we're trying to cancel these out so they have to match. If I take a look at my periodic table, I will find that the molar mass of N2 is 28. Okay, and molar mass is always 1 mole. So 54 divided by 28, my answer is 1.93. Okay, so this would be a very intimidating problem if you didn't outline the information. It might be difficult to figure out where to start, where you're going to plug things in. But because we've already outlined it, now I'm just going to plug in all the information that I know. So I don't know the pressure, so I'm just going to call that X. My volume was 10 liters. We're going to leave out units for now, but if you plug them in, you'll see how they cancel out, and you'll be left with atmospheres. And then we're going to plug in moles, which we just solved for. 1.93 times the gas constant, 0.821. And then we're given our temperature in Kelvin. All right, so I'm going to combine these terms on this side. 1.93 times 0.0821 times 298 equals, I'm going to flip that, 10x. 10 times x and x times 10 is the same thing. Okay, and then I'm going to divide both sides by 10. X equals 4.72 atmospheres. Okay, and I know that I'm left with atmospheres because the unit for pressure in my gas constant is atmospheres. So this will also be atmospheres. Okay, so let's check out sig figs here. This one had 3, 3, 3, and my answer has 3. So we are done.